So this lesson is going to be all about time of flight mass spectrometry. Remember guys, A-Level exams are a game. Everything you see on the screen right here is what you need to know for the AQA specification. Now, essentially what I'm going to cover in this video is all of the stages and information of the time of flight mass spectrometer you need to know, as well as some stuff surrounding calculation questions. Okay, then at the end of the video, I'm going to do some active recall of a few points just to make sure that you're paying attention and actually putting in that work to improve your grade. So TUF mass spec then. What is the function? We briefly touched on it just now in the specification. Its function is to identify elements by determining all of the isotopes present within a sample. Okay, and again, we're going to go through the 5 stages quickly. Do your best to remember these, and we'll go through some key details of each stage. So we have stage 1, ionization, stage 2, acceleration, stage 3, ion drift, stage 4, ion detection, and lastly, we have data analysis. Okay. A really important thing to remember here is the conditions, okay? The conditions for any mass spectrometry, including time of flight, is they must be kept under a high vacuum. Why is this? What is the purpose? The purpose is to prevent the ions that are produced in the process from colliding with molecules present in the air. This would completely mess up your mass spec, so we really want to avoid that at all costs. So, ionization. This is the first stage we're going to be looking at, and there are 2 types that you need to know the difference between. So first off, we have electrospray ionization. So what happens in this process? The sample is dissolved in a volatile and polar solvent. Okay, it's really important that you remember these keywords, volatile and polar solvent. Okay, so what happens here is it's dissolved in the sample and then it's injected at high pressure, another really important keyword, through a fine hollow needle connected to the positive terminal of a high voltage supply. What does this do? It causes the tip of the needle to have a high voltage. Okay, so this solvent with the sample in it is sprayed out of this needle at very high pressure with a high voltage. What does this cause it to do? It causes the sample, in this instance, I'm just going to refer to it as molecule X, okay? Just to represent any sort of typical molecule that we're looking at analyzing, and it gains a proton from the solvent, okay? The solvent is going to be the source of the proton, the H+ ion, and it forms a XH+. Now remember that X can be any molecule that you're looking at, but it's essentially forming an ion that is positively charged by gaining a proton, okay? You need to know the equation for this. What is the equation for electrospray ionization? So we've got any source of molecule, isotope, whatever we're looking at, X, and this is gaseous. Really important that you remember this, but it's a super easy equation. You just add a proton to it, okay? And it forms XH+. Whatever X is, don't put X in your exam. Whatever they're referring to in the question, put that in the space of X, okay? But really remember the state symbols. It's really important, okay? What happens next is really important, guys. The solvent evaporates, okay? The solvent that the sample was dissolved in evaporates into the vacuum. Remember I said this is under a vacuum, is the primary condition you need to remember, while the positive H+ ions, which are connected to the molecule that you just formed, these do not evaporate, okay? And they're going to hit the detector, which we'll look at in a second, okay? Now, remember I said there's 2 types of ionization. What would this be used for? Is going to be used when analyzing large organic molecules. Why is that important? Why do we care that this is used with a specific type of molecule? It means that fragmentation does not occur, okay? If you have a really large organic molecule and you do the other form of ionization that we're just about to look at, you'll fragment it up into tons of little pieces and it will just make it so difficult, essentially impossible to identify what molecule you're looking at. So let's look at the next form of ionization. This is referred to as electron impact, okay? There's 3 primary pieces of this that you need to be aware of, okay? We have the injection nozzle, pretty much exactly the same as the previous form of ionization. You have an electron gun, not really a gun, it's just a heated coil, okay? But we'll look at that in a second. And then you have what's referred to as an electron trap. This is just a positively charged plate that's going to attract the electrons from the electron gun towards itself. Okay, so what happens here? The sample again is vaporized and injected at low pressure. Now you'll notice that it's not dissolved in a solvent. That's important to remember the difference there. What happens next? So this electron gun right here, it fires high energy electrons at the injected sample. Okay, and these electrons, if they hit one of the isotopes in this sample or molecules, whatever you're looking at, if they hit it, it's going to fragment, okay? It's going to become ionized. And the way that it's ionized is an outer electron is knocked out from each particle, okay? So the outer shell of electrons, electron hits it, it knocks an electron away, and it forms a 1+ positively charged ion. Again, there's a formula you need to remember here. It's X gives us X plus electron. Both gaseous, again, okay, state symbols are really important here. They will penalize you if you do not put state symbols. Again, I've just used X as any element, any isotope, whatever you're looking at, but just remember to fill in the correct one in your questions. So what is this type of ionization used with? It's used for elements and substances with low formula mass. Okay, just try and remember that. It cannot be used with larger molecules. This is really important. They may test your knowledge on this. Remember, I said it will cause it to fragment. Because of the electron gun, it's going to fragment it apart, and you do not want that to happen with larger molecules. You just want it to be the case with particles with low formula mass so that they can be ionized easily. Right, next up, acceleration. This is the next portion of the time of flight and mass spec. So what happens? We have two portions that you need to be aware of. Really simple stuff. We have a positive plate and a negative plate. Okay, these are just positively charged and negatively charged. Now what happens here is that the positive ions formed from either ionization method, okay, there's only one form of acceleration. These are accelerated to a constant kinetic energy. This is really important to remember. Constant kinetic energy by an electric field. So they're accelerated towards this negatively charged plate. That's why it's so important that they become positive ions. Otherwise, there's going to be no attraction towards the negative plate. Okay, so the ions won't be accelerated, they won't move. Now, I mentioned that all ions have constant kinetic energy. This is really important. So maybe some of you noticed that the green, smaller positive ions traveled faster towards the negative plate than the slightly larger positive red ions, okay? And this is because lighter ions will travel fastest since their velocity or their speed, but try and remember the word velocity, is dependent on their mass. So lighter molecules will travel faster and will hit the negative plate or pass through the negative plate sooner, whereas the more heavy or higher mass molecules, particles, whatever you want to refer to them as, will travel slower and travel through the negative plate more slowly. Really important you remember this. They will potentially ask you questions on this. Right, acceleration done, ionization done. Let's look at the next stage, which is drift and detection. Okay, so we have another portion of the mass spectrometer here. So this is the negative plate. That was the portion of the acceleration stage. Okay, so nothing's changed here. It's just a negative plate. But you also have another plate, which is, or sometimes you'll see it as a box, and this is a negatively charged detection plate. Okay, now I've tried to represent this by just drawing a ton of electrons on it. Okay, and we'll see why that is in a second. But this is where the isotope is ultimately, or the ion is ultimately detected. Okay, and you're going to use that for your analysis. Now, what happens here is the positive ions pass through a hole in the negatively charged plate, forming a beam. Okay, almost like a laser beam. Now, these electrons are going to fly through. As I mentioned, the lighter particles, molecules, whatever, will travel faster than the heavier ones. Okay, now they're going to travel along this region or a tube called the flight tube. Okay, and they're going to reach the negatively charged detector. Okay, it's just another negatively charged plate. Plates all over the place in mass spec, all right? Just try and remember the distinction between whether they're positive or negative and you'll be all good. So what happens is the positive ions reach the negatively charged detection plate. and they gain an electron and produce a current. Okay, so they gain this electron and they produce a current. Why is this important? Current is simply a flow of electrons from the plate to the ions. Okay, the positive charge is accepting that negatively charged electron onto itself, and that movement or that flow of electrons is what forms the current. Okay, why is this important? It's actually pretty clever. The amount of current produced is proportional to the abundance of the species. Species just essentially means molecule, particle, ion, isotope, whatever the hell you want to refer to it as, whatever you're looking at in your sample. The more current that is produced, the more abundance of that thing. Hopefully that makes sense. Right, last stage here, data analysis. So there's two pieces of information which are analyzed in combination once you've finished running the mass spec, okay? First one being what we just looked at, the current that is produced, okay? The amount of current that is produced. The next is the flight tube times, okay? Time of flight, that's why it's referred to as time of flight mass spec. How fast did that ion travel? That's another key piece of information they're gonna look at. So what does this allow scientists to do? It produces a spectra with the relative abundance produced by the ions with varying mass charge ratios, okay? This is just an example mass spec of tellurium, okay? And you can see on the y-axis, we have our relative abundance from 0 to 7. This will change depending on the ratios of the abundance, right? And then on the x-axis, we have the mass to charge ratio. If you're a bit baffed, a bit confused, don't stress. I'll go into far more detail in the mass spec and relative atomic mass video. You honestly don't need to know about it right now for the time of flight side of things, but I just wanted to show you so you had a brief glimpse at what it looked like when you're analyzing the data, and you will have to be able to do this when it comes on to mass spec questions. Right, that's the 5 stages done, guys. Let's look at some calculations and equations, and this will come into play when you look at the ionic drift portion. Okay, so there's two important equations that you need to be able to understand. The first one is Ke equals half mv squared. I'll go into what the individual variables are in a second. This one is pretty much always given to you. Okay, the second one, on the other hand, isn't always given to you, and that is T equals D over V. So what do these stand for? Easy stuff, guys. Ke is just kinetic energy. Energy given the units joules, all right? Then we have mass, this is in kilograms. And then we have V, which is our velocity, or simply our speed. How fast does the ion travel down the flight tube, okay? This is in meters per second. And then for the second equation, we have the time of flight, which is our T, and this is just simply how long does it take to reach the detector, and that's in seconds. Then you have distance, okay? How long is the flight tube? All right, distance, length of flight tube. In questions, it will often be asked or referred to as length of the flight tube, and this is in meters, okay? And then V for equation 2 is exactly the same. Velocity or speed. I'd try and get into the habit of using V and velocity in your equations. That's what AQA would prefer to see. Now, something really, really important here, guys. Remember this unique unit of mass for the time of flight mass spec topic, okay? Normally, mass in any other topic is going to be given as grams. This is really important to remember. If you skip your revision for time of flight mass spec and these sort of 5-6 mark calculation questions, you're going to miss out on a few marks here just because you do not convert the mass from grams into kilograms, okay? Remember this unique caveat and you should be all good to go. So if they give you equation 1, why did I bother telling you it? Why do you need to understand it? You need to be able to rearrange it as needed, okay? So they can ask you for any of these variables in the question. They can be like, what's the time of flight? What is the velocity of the ion? What is the mass of the ion, etc. And they need you to be able to rearrange the equation, okay? Master this fundamental ability. Across all calculation-based topics of A-level chemistry, this is so important. I cannot emphasize that enough. If you master the fundamentals of rearranging equations, it will just save you so much time and so much stress, all right? So work on that and you'll be all good to go. Next up you need to be able to combine these two equations together in some way. And this is question specific, okay? Depending on what variable they ask you for and what information you're given in the question. So for example, you may need to plug in the variable of velocity into the time equation, right? Hopefully that makes sense. And again, if you're a bit confused, do some practice questions, okay? Calculations, just like maths, you need to do these past paper questions, okay? So watch some YouTube videos, do some past paper questions, and you'll be completely fine. Right, guys, so this is where you take what you've just learned and apply that information to some active recall. Okay, active recall combined with past paper style questions is gonna boost your grade so much, right? So there's 3 questions here on the screen, and there's another longer question that we'll look at after this. But do your best, guys. Pause the video and attempt these questions the best you can. Right, question 1. What condition must the whole mass spectrometer apparatus be kept under, and why? Do you remember why this is? And the reason for this is to prevent the ions that are produced from colliding with molecules present in the air. So remember, we have 2 different forms of ionization that can be used. Ions are going to be produced, and these ions can potentially collide with molecules that are in the air. That's why we have a vacuum. Okay, question 2, describe what occurs during the acceleration stage of TOF mass spec. So the answer you should have got here is along the lines of the positive ions are accelerated to a constant kinetic energy. Remember those keywords, guys, constant kinetic energy, by an electric field, okay? Electric field, not magnetic field. This is a very common incorrect answer. So just remember electric field, and this is towards a negatively charged plate. So remember, positive ions are attracted to the negatively charged plate. Right, question 3. In the detection stage, what is the amount of current produced proportional to? So it's proportional to the relative abundance of that ion. All right, so this is 3 easier questions out of the way. Let's look at a bit of a more long form question. Describe what occurs in electrospray ionization. So there's multiple points you need to get here, multiple keywords in order to get all the marks. So in electrospray ionization, the first step is going to be that the sample is dissolved in a volatile and polar solvent. Okay, volatile and polar, those are our key words. Now, once it's been dissolved, it's then injected at high pressure through a fine hollow needle, which is connected to the positive terminal of a high voltage supply. And this causes the tip to have a high voltage. Okay. Now, if you want to shorten this down a bit more, you could just say it's then injected at high pressure through a fine needle with a high voltage. That's all you need to say there. Okay. So what does this do, right? This causes the sample molecule X to gain a proton from the solvent, ultimately forming that XH plus ion. Okay, remember, don't put X in your exam, replace this with whatever you have in the question. Really important mark here, it's demonstrated by the following equation. Remember this equation, super important. Last point here is that the solvent evaporates into the vacuum while the XH plus ion moves towards the negative plate. So hopefully you guys got a decent amount of that correct or remembered as much as you can. Take that and apply it to some past paper questions. There's only a limited number of questions they can ask you guys. Right, summary and spec check. Let's make sure we tick off everything we need to know. So I went through the different stages you need to be aware of, as well as all of the underlying explanations and things to remember. So we went through ionization, we went through acceleration and the key point of constant kinetic energy. We went through ion drift, ion detection, and the last stage of data analysis. We also took a look at the example of the tellurium mass spec that would be given out just to see how mass spec gives accurate information about relative isotopic mass and about relative abundance. And also lastly here, mass spec can be used to identify elements. Real simple points here. Again, this was the time of flight side of things. If you want to look at a video that's regarding mass spectrometry and relative atomic mass as a whole, I've made a separate video on that entirely. If you're not too sure where to take your revision next, guys, I highly recommend checking out my what topics to focus on videos for papers 1, 2, and 3. It's going to help you realize which topics come up the most and where to focus your revision.